Hey there, how's it going? Terry Brown, Mechanical Engineering here with another Engineering Mechanics video. Today I'm going to look at working out the reaction forces on a motor. So let's have a look at the problem. All right, so here you can see the problem. So I'm just going to go through the problem pretty quickly, just as it's written from the textbook. But then afterwards, I've got a few little motors here that we on my desk, and I'll have a look at those and talk about a few other things at the end of the video. But firstly, I'll just go through the problem quickly, and then we'll talk about some other things afterwards. All right, so here we have this motor. You might not recognize that as a motor. Hopefully at the end, when we look at some actual little motors that I've got in my office here, it'll become a little bit more obvious. But anyway, we've got this couple moment that's applied to the shaft of the motor. And then because of that, we need some reaction forces down here at the bolted connections where the motor is bolted to the ground. Right? And we want to know the magnitude of these reactive forces. So our solution is, if we know our equation for moments or for a couple, so if we know that we've got a couple, then we know that the magnitude of the couple is equal to the magnitude of one of the forces, or they're both the same. So the magnitude of the force that forms the couple times the distance between the two forces. So we'll just use that. And in this case, we want the resultant of this moment, or this couple, to be equal to the couple that's generated in the support. Right? So we want the net moment to be equal to 0. And I'm going to assume anti-clockwise is positive. Right, so putting that in, we've got the applied moment that's applied to the shaft is in the clockwise direction. So according to what I've assumed here, that will be negative, plus R times D, which is our couple that's formed down here. So we need to know this distance here between the two bolts at A. Right? So you can see that it's just R times D. We don't, if we take moments about point A, we have the moment here clockwise, negative, plus R times this distance here. Right? And this one will cause no moment because we're taking moments about point A. Same as if we take moments about point B here, we'll have this force here tending to rotate anti-clockwise about point B. Here through point B has no moment about point B because the perpendicular distance is 0. So we can think about it in a number of ways. All right, so let's rearrange that equation. Moment equals R times D, and we just need to work out our distance, and that's already come up for you, so let me just explain that. So I need to work out this distance here between the two forces. We're given this vertical distance, 150 millimeters. So if we just have our little triangle here, right? So we know the hypotenuse. We need to know this length down the bottom. So if we've got 60 defined there, this is our adjacent side. So therefore that will be, actually we don't have the hypotenuse at all, do we? It's a little bit tricky. So we've actually got the opposite here, right? So we know that tan of an angle equals opposite over adjacent. Okay, so that's all I've done in order to calculate my distance down here, which would be the distance D that I've got in that equation. And we've got 2 of them, so that's why it's multiplied by 2 over here. All right, so let's continue that. So if we do the maths, we get that distance there is 173.2. Okay, so that's that complete distance here. And then rearrange our equation that we had up here to solve for our unknown reaction force R. And we get on top, we've got our moment was given as 5 Newton meters, which is also, convert that to Newton millimeters because we've got our distance up here in millimeters. So that'll be 5 by 10 to the 3 Newton millimeters, okay, because there's 1,000 millimeters in a meter, divided by our distance that we calculated before, 173.2. That's in millimeters. So that'll give us an answer of 28.87 newtons. We can round that up to 3 significant figures, 28.9 newtons. All right, so that's the answer to the problem. So we've worked it out. Now let's have a think about what this all means, right? Often in these textbook problems, you're told to do something, but you're never really told why. Okay, so what I'll do is unshare just for a second. Have a look at some motors that I've got here. So here's a little, so I think this is a little DC motor. And what you're seeing in the picture in the diagram that we just did the problem solution for, you're looking end on like this. So here's the shaft. So you can see if I put it up a little bit closer here, right, this bit here, right, there's our shaft. And this is a pulley on here, so you have some kind of a belt on here. So we're going to have some kind of a torque being generated on that shaft. Right? So when we do that, that gets reacted into these two mounting holes here, similar to what we had up here. Right? So instead of in my little motor that I've got here, the mounting points are up here next to the shaft. In this case, they're down the bottom. Here's another one. This is a little stepper motor, and you can see this has got a flat on the shaft here, so you can attach something to that and then rotate that. Can't turn a stepper motor. Yeah, so that's where the torque would be, and then that moment would be resisted by the supports here. Okay, so we need to design, for a little motor like this, it's not going to, any screw you find in or bolt that you find in the Bunnings or workshop is going to be enough. The thing you might need to consider though is these little tabs on the outside here. Assume when whoever designed this little stepper motor, this is quite thin. So as a design exercise, you would need to know, right? Same as we did in the problem that we've just looked at. We could work out a force up here and a force down here, and then calculate the stress that's developed in these little tabs here, and make sure that they can carry the load that's developed by putting a torque or a moment on the shaft. And our other little one that I've got here, a little DC motor. Here you can see you've got a gear on the end. That would be attached to another gear. You'd have a contact force between the two gears, and then that would generate your torque on. I can, because this is a DC motor, I can spin this. So if I actually spin this, you should know if I connected this up to a resistive load, then this is going to generate some power. Right? So you can use the motor in reverse as a generator. All right, so let's go back to our problem. The other thing to consider here, so this is quite a large motor. If this motor was sitting on a beam like that, and it might be simply supported at one end, roller support at the other. There's my motor sitting on here. I'm just doing it in dotted lines. What we would have acting on that beam then would be the equal and opposite of what we've got acting on the motor. Right? So we would have loads like that acting on our beam. So then we've got an input into our beam design problem. So then you need to work out the size of the beam for strength and deflection. Also with a motor sitting on here, right? This is going to be, if there's some out of balance, this is going to generate a force up and down like this. So then you need to make sure that the frequency of this rotation doesn't match the natural frequencies of the beam. Okay, and you'll do some subjects, if you're doing an mechanical engineering degree, either UTS or anywhere else, you'll need to look at calculating the natural frequencies and the mode shapes of the structures that a rotating machinery like this will be sitting on, right, to make sure that you don't set up a resonance in that beam. All right, so that's it for this problem. plus a little bit of extra application to make sense of what it is that you're doing here. So hopefully that was interesting and helpful for you. If you like my videos and the longer descriptions that I provide, then please like the video and maybe even subscribe, just so that the YouTube algorithm sees that and suggests it to more people. Okay, I'm not making any money out of this. I just do this all for free. But yeah, so thanks for hanging around, and I hope you enjoyed that, and I'll catch you. Bye for now.